Okay, so let us start.
Maju Ladai.
Okay, so we started discussing Laplace transforms yesterday. So let us continue. So today we will discuss ROC more in detail and some Laplace transform properties also, and possibly some connections with systems also regarding Laplace transform. So let me continue with some examples we were discussing yesterday. I think we saw this second example also yesterday, if I remember correct. Yeah, I think we did these two examples. So both causal. One situation is where A is positive and the other where A is negative. So I hope this is fine. So let us consider anti-causal cases now. So we have u of minus t now in both these examples, and A is positive and negative respectively cases. So let's check these out one by one. So yeah, since we have u of minus t here, the interval of integration is now from minus infinity to 0, because this is 0 for the positive half. Okay. And we have this this integral to evaluate. So t is negative now, and yeah, we want this integral to be finite. Okay. So there is a negative sign in here, and t is also negative. So for this to be finite, we want the real part of minus s plus a to be positive, right? Because if this quantity is positive and yeah, since t is negative, this is going to die out, and this is going to be integrable. This is ensured. Okay. So ROC will be minus of s plus a strictly greater than 0. Okay. So proceeding forward, so you can do like this, or maybe this is better. So real part of minus of s plus a is greater than 0. So this being greater than 0 is same as this being less than 0, and then this implies real part of s must be less than minus a. So yeah, this is what I am doing here. So yes, I made some mistakes, and yeah, I think this is correct. Okay, so you guys can also check this properly. So yeah, yeah, I think this is correct. So these signs can be confusing. They are confusing for me, and they are confusing. They might be confusing for some of you as well. Yeah, you just need to do it carefully, and yeah. So this is the ROC. Since A was taken to be positive, minus A is yeah, in the left half. So I hope that is what we have here. So yeah, real part of S to be strictly less than minus A. Okay. So this is the region of convergence for this case. So for causal signals, if you remember, we had yeah, right half regions. Okay, so wherever so yeah, this is called pole of A. I will make that more precise. What do I mean by pole and so on? But yeah, everything to the right of the pole is what ROC is for causal signals, and yeah, for anti-causal signals you have everything to the left of the pole. Okay, so yeah, what is pole and zero? Yeah, we will come to that today. So I hope this example is fine. let's take this other case also where A is negative. So yeah, it's more or less the same. You just have to be careful with signs. Okay. So now, yes, we have the same expression. Only thing is A is negative. So I think someone has started another meeting, but yeah, you can let them know that yeah, we are meeting here, and, not PKD sir's meeting, because I am unable to share my screen using that meeting. Okay, so proceeding similarly, we again have real part of s less than minus a. Okay, just following through the same steps, but a is negative in this case, so minus a will be in the right half. Okay. So this is the ROC for this signal. Again, it is to the left of this vertical line. So yeah, these are two other cases of anti-causal signals, and now let's consider a mixed signal. Okay, so yeah, this is both. So yeah, neither causal not anti-causal. Okay, so in the positive half we have decaying exponential. Okay, so for t greater than or equal to 0, the signal is given by this expression e to the power minus at ut. A is positive, and in the negative half it is e to the power at u of minus t. Okay. So why it is decaying? Because yeah, since a is strictly greater than 0, and yeah, here t is negative, you get a decaying exponential in both halves. So what is the ROC of this is the question. Okay, so let's apply definitions. Uh, so from 0 to infinity, yeah, we have this expression. So uh, yeah, you have this integral to evaluate by substituting this expression for x5 of t, and yeah, over the negative interval you have this other expression. So here you will get 1 over s plus a, and here you will get 1 over s minus a with a proper sign, okay, plus or minus. So yeah, I leave it to you guys to check that out. Okay. So as seen in the previous four cases, ROC for this integral to converge is real part of a to be strictly greater than minus a. Okay, so everything to the right of minus a is positive, so minus a is in the left half plane. Okay. For this integral to converge, ROC is given by this quantity. So real part of s strictly less than plus a. So just check that this is consistent with what we have done here. So let me see this. So a was negative here, so it's minus a. We take that to be b, then b is positive, and yeah, real part of s is strictly less than b. Yeah, is what we get. Okay, so yeah, just using that argument, yes, we have ROC given by real part of s to be strictly less than plus a. Okay, so everything to the left of this vertical axis, and the region where both integrals converge is just the intersection of the two ROCs. Okay, so that region is given by yeah, uh, this this shaded area. Okay, so everything between minus a to plus a, these two vertical lines is where this entire integral will converge. Okay, so in this part to the right of plus a, this integral will converge, but this will not converge, and similarly in this half, this integral will converge, but this will not. Okay. So there will be cases where you may have ROC to be empty. Okay, so that can happen in general, or you may have some non-trivial intersection. Okay. Yeah. Any question? Okay. So yeah, I hope this is fine. Okay. So in general, if you have mixed expressions of causal and anti-causal and this two-sided signal, yeah, just by looking at yeah, the sign of t and the sign of whatever you have as multiplying t, you can figure out the ROC. Okay, and if you have multiple signals, then yeah, you need to take intersections and you need to make sure that all integrals converge. Okay, so if the intersection of individual ROCs are empty, then okay, you have convergence nowhere. So Laplace transform will not exist because the region of convergence will be empty. But if it is non-empty, then okay, you can then identify the specific region where the Laplace transform converges, and that will be the region of convergence. So I hope this is fine. Okay, so let me come to poles and zeros now. So we have a transfer. So I have not defined a transfer function yet, but yeah. If you have a Laplace transform like this, so let me define transfer function also. So transfer function is the Laplace transform of the impulse response of an LTI system. Laplace transform of h of t. So h of t is the impulse response of my system, LTI system. So this is h. Hello, can you guys hear me?
Yes,
Yes,
sir.
sir. Yes,
Okay.
sir.
So I the connection. Okay, good. So this is the impulse response, and you know that x is my input, then y is given by x convolution with h. So this is h of s. Okay. So this is what we call as transfer function of this system. Okay. And now by convolution multiplication property, we have not shown this, but yeah, we will show this. This is x of s times h of s. So transfer function of an LTI system is the Laplace transform of its impulse response, and yeah, transfer function is only defined for LTI systems. Okay, linear time invariant. For linear time varying systems or non-linear systems, you don't have transfer functions or Laplace transform. Yeah. So yeah, this makes sense only for LTI systems because you have this convolution multiplication property. You can take Laplace transforms and so forth. Okay. So if you have a rational function like this, okay, P of s over Q of s. So if this is my transfer function, so both P of s and Q of s are polynomials, then zeros or roots of P of s and we also have roots of Q of s. these are zeros. Let me call them Z, and these are poles. I will explain why these are called poles. Sort of intuitive, but yeah, just hold on to these cases. Okay. So I hope this is fine. What are poles and zeros? You have an impulse response. You take its Laplace transform, and if you get a rational function like this, then yeah, poles of roots of the numerator polynomial are called zeros of this transfer function, and roots of the denominator polynomial are called poles of this transfer function. All right. So zeros is fine. Why these are called zeros? Because these are the points where put it like this. Okay. Okay, so these are the points where the transfer function becomes zero. Okay, so everyone knows that yeah, if you give this as an input to an LTI system by convolution, what you get at the output is h evaluated at s naught times the same complex exponential. All complex exponentials are eigenfunctions of all LTI systems. So yes, if you feed in any complex exponential, you can apply convolution, and then using definition of Laplace transform, you can show that this is what you get. Okay. Now, if S naught is a zero of your transfer function, then this quantity will be 0. So it does not allow complex exponentials at zeros of the transfer function to pass through this system. Okay, so the system response is 0. Yeah, this is one way to look at it, and the other way is yeah, just because h of s vanishes at these specific complex number, they are called zeros of the transfer function. Similarly, for poles, yeah, you can see this is going to diverge at poles. Okay, so h of p naught is going to be infinite at poles. So, sorry, this is infinite. Okay. So if you draw, so this is my S plane, and this is magnitude of h of s. So imagine this in 3D. Okay, so this is your S plane, real part and purely imaginary part, and the magnitude is what we are plotting against yeah, these complex numbers. So if suppose we have a pole at this point, okay, so this is our pole. I'm explaining why it is called pole. Okay, so at this point the response goes to infinity like this, like this. So imagine this in 3D. Okay, if you have multiple poles, then yeah, you will have this shape repeated at those points. Okay, so the magnitude is finite everywhere, but yeah, at these specific points it shoots up to infinity. So yeah, this looks like a pole. Okay, so if you are familiar with poles on the street, light poles, so yeah, these are these tall shapes like that. So yeah, using that analogy, yeah, this is something like a pole. So that's why these points are called poles. Nothing deep or anything in that definition. All right, so I hope that is fine. Poles and zeros. All right, so let us continue analyzing ROC a bit more in detail. So let me show you these properties. So you can also see these things discussed in more detail in Oppenheim's book with some examples also. But yes, these are not too difficult to grasp. Okay, so let's discuss these one by one. So first property is as follows. ROC consists of steps parallel to j omega axis. Uh, I hope this is easy enough to understand, right? So we want our Laplace transform integrals to converge. So x of s, which is x of t, integral is from minus infinity to plus infinity. Okay. So if the signal is right-sided, for example, we have seen that we have to then, yeah, if it is a complex exponential, yeah, you get something like this. A is positive. If the signal is right-sided, then yes, you always have your ROC to be on the right of yeah, your pole. Okay, so this is our pole, for example, in this situation. And if you have multiple signals, so e to the power minus a1t ut, let me not write u of t, writing u here, plus e to the power minus a2t u of t, like that. Yeah, you will have a1, a2 like that. A2, for example, is a1. And individual integrals will yeah, converge yeah, either to the right of a1 or right of a2, and for the entire sum to converge we have to take everything to the right hand side of the pole. If there are no poles, okay, so for example if your xt is something like this, okay, so it only has it exists only over a finite interval and finite everywhere. So this is my xt. So what happens to this integral? This is one of the properties. The integral, whatever the complex, this is now just over this interval. So let's say minus t1 plus whatever t2 x times e to the power. Okay, so no matter. Okay, so yeah, anyone has any suggestions? What will be the ROC of this case? The integral is just over a finite interval. The signal is finite at all points. What about this quantity? Is it staying bounded or is it getting unbounded within this interval? X is bounded, we know for sure, and finite everywhere. If both quantities are bounded at finite everywhere, then this integral is going to converge for all x. So if t is finite, then e to the power minus st is always bounded and finite. Okay, so yeah, so complex exponential. So I cannot draw it. I can only draw real exponential. So even if they are growing, decaying, but if you restrict them to some finite interval, this integral is always finite. So this This is I am showing for real integrals, but even for complex exponentials, if you restrict them to finite interval, the integral is always finite. So in this case, yeah, both these are integrable over finite interval. So yeah, this integral is always finite everywhere. So no matter what s you choose, this will always exist. This is I think one of the properties. Yeah. If x of t is of finite duration and absolutely integrable, then ROC is entire S plane. Okay. Because your integral converges everywhere. Second property is ROC does not contain any poles. Yeah. This is just common sense. Okay. Uh, the integral diverges at poles. It becomes infinite. So of course ROC cannot contain any poles. So first three properties, I hope everyone follows why they are there.
Sir,
Yes.
sir, can you please explain the ROC, the first property once more?
Okay. So yeah. Yes. So suppose we have rational functions like this. So let's say product of so this is over I. And this is product of
Sir, your voice is not clear.
so yeah. So what I was saying is yeah. Suppose we have a transfer function like this, rational transfer function, which is a product of zeros like this. So both of these products are over I. So zeros are Z1, Z2 up to Zm maybe, and poles are P1, P2 up to Pn, for example. Okay, so let's locate poles first. So they are specifically the points where yeah, the Laplace transform diverges. Okay, so I've drawn too many, but so P1, P2, P3, P4 like that. Suppose those are our poles. So this is P4. We not write P2 and P3. Okay. So xt. Uh, yeah. For example, if xt is causal, so yeah, all these exponentials are right-sided, then yes, you will get strips like this for individual integrals to converge. Yeah, and all four integrals they will converge only at this point. Okay, so everything to the right of P4. This is where all four integrals will converge. On the other hand, if you have mixed signals, okay, so both causal and anti-causal. So P1, let's say, yeah, this was an anti-causal signal. So suppose you had an ROC like that. P2 was here. So P2, P3, and P4. So corresponding, my x of P is sum of x1, x2, etc. up to x4. Where yeah, these are obtained by taking inverse Laplace transform from here by using partial fractions. Okay. So if x1 was anti-causal and you had an ROC like that, x2, x3, and x4 are causal. So yeah, you had ROCs like that for this. So in this situation, ROC will be empty, for example. On the other hand, yeah, if this is another case. So P1, suppose x1 was causal. Here we took x1 to be anti-causal, but if x1 is causal, and let's suppose x2 is anti-causal. Something like this we will get, and let's suppose these two are also anti-causal. So the ROC looks like this, and this is the intersection which we get. If all of them are anti-causal, then yes, everything to the left of P1 is our ROC, and like that. So depending on where your poles are and whether your signal is causal or anti-causal, you have this uh, half plane. So what I mean by half plane is as follows: you you first locate where your pole is, and depending on whether your signal is causal or anti-causal, your ROC will be everything to the right of this or everything to the left of this. If there are no poles, then yes, your Laplace transform converges everywhere. Yeah. So this will happen only when there are poles, and we are dealing with the cases where there are just finitely many poles. Okay. So locating poles is the first step, and the next step is whether your component, so your signal in general is time domain signal is, yeah, this sum of these components, each having a pole somewhere. So whether each component is causal or anti-causal, depending on that, yeah, you will have either everything to the right of that or everything to the left of that. So this is I'm saying this is as half plane. Half. So this is right half plane, for example. Similarly, you have left half plane. So for vertical axis, yeah, real part of S greater than 0 is the right half plane, and this is the left half plane. Okay, so you have these half planes for single poles. Okay, so if there are no poles, then fine. Your Laplace transform converges everywhere. ROC is the entire S plane. Okay, so this is when there are no poles. No poles. Okay. If there are poles, like this, for example, okay, finitely many. We will only deal with the cases where there are finitely many poles. You use partial fractions and separate these things out, and depending on whether your signal is causal or anti-causal, yeah, once you locate the pole, the ROC for that specific component will be either the right half plane of this pole or the left half plane. Okay, and finally, to find the ROC of your entire signal, you need to take intersections of these ROCs, individual ROCs. In other words, you need to take intersections of these individual hyperplanes, half planes, I'm sorry. So, yeah. In that, I think, yeah. So I hope this is fine now, why ROC consists of strips parallel to j omega axis. Okay, so what do I mean by that? And yeah, I have also explained these properties also, but let me come back to that a moment later. So let me clear this. Okay, so ROC can look something like this. Okay, we have seen. So strips parallel to j omega axis, I mean, yeah. So all these strips are there in your ROC. Okay, your ROC looks something like this. So then all these strips are there up to infinity. Okay, so everything to the right is there in ROC. Yeah. So all these vertical strips belong to the ROC. This is what we mean by ROC consists of strips parallel to j omega axis. Okay. So ROC can be yeah, empty. It can be the entire complex plane if there are no poles, or it can be this right half plane. Okay, so you take some P1, everything to the right of that is your ROC. It can be something like this, everything to the left of something everything between P1 and P2. So your ROC will be one of these 5 types. Okay, it cannot be something different from this. And strips parallel to j omega axis. I hope that is clear. So all these strips are in the ROC. If your ROC is the entire complex plane, then okay, you have all translations of the purely imaginary.
Sir, what is the second type?
Second type is the entire complex plane. So this is boldface C. So this is complex plane.
Sir, which means our the Laplace transfer will not be convergent anywhere.
No, it is convergent everywhere. If the region of convergence is empty set, then it is not convergent anywhere.
Understood.
If it is the entire complex plane, then it converges everywhere. No matter what S you take, the integral converges. So this is one example when your signal is of finite duration. In that case, ROC is the entire S plane. All values of S it converges. If you have poles, then you don't get the entire complex plane. You can get empty set if there are multiple poles, and if your signals are both sided. If your signal is one sided, then you will fall in either this type or this type. Okay, so that also maybe I can list. So this is for right sided. Right sided. This is for left sided. So right sided or causal. Okay, so causal signals will have ROC like this. This is for anti-causal signals, and this empty set or this bounded region. This is for both sided. Okay, for both sided signals you can have this finite strip, so finite along x-axis but infinite along y-axis, or it can be empty. Okay, so for causal signals ROC will never be empty, and can never be this also. Causal signals can have this as ROC or this as ROC. Anti-causal signals can have this as ROC or this as ROC. So by anti-causal, I mean, they are identically 0 for T positive, only exist for negative T.
Sir,
Yes.
sir, for a causal system, why the ROC is right side to the pole? Is
No,
it
I
a
could.
condition or we have assumed it?
Sorry, can you repeat? I could not hear that.
Yes, sir. Sir, am I audible now?
Yeah, little faintly, but yeah, I can hear you. Please go ahead.
Yes, sir. Yes, sir. Sir, I am asking for a causal system, why the ROC is right side to the pole? So, is it a condition or we have derived it? So, you have just explained before.
We have seen this, right? So if
Yes,
you're
sir.
causal, then everything to the right of this, because we want S plus A to be positive. Okay, so even if you have negative A, in that case you want this S minus B to be negative. Okay, so let me explain this property. Okay, so suppose my signal is right sided, yeah? So X is causal. And suppose I have one pole. So for simplicity, I'm just taking one pole. Okay, you can have multiple poles also. So let's do that case first. Suppose let's do both cases together. So suppose I have one pole like that, and we have seen that everything to the right of this is ROC. So yeah, why is that? So if P1, let's take P1 to be positive, so P1 is equal to A, then this integral to converge, we want S plus A to be positive, and that boils down to uh, real part of S to be strictly greater than minus A. Yeah, this is minus B. Let me erase. Alright, so this was our pole, and we want yeah, real part of S plus real part of S to be greater than minus B1 for this integral to converge. So if we take any point, so any vertical line, for example here, which has suppose this is sigma, and real part of so sigma is real, so sigma is strictly bigger than minus P1. Then you substitute that in here, you are going to get convergence. Yeah, just convince yourself that if I keep saying that, yeah, I will confuse myself and I will confuse others also. This just follows from definition. Okay, where was I? Yeah. So yeah, just give it a little thought. Everything to the right of that. Just take any vertical line and y integral should converge here. You can convince yourself why this should work. Okay. So for causal signals, yeah, if you take any strip to the right of this pole, you are going to get convergence. That's why it is going to be in ROC. If you have multiple poles, all, so if your x of t is causal and yeah, you have multiple poles, then for those individual components, yes, you are going to get this right-sided ROCs. And when we take intersection, we are going to have everything to the right of the rightmost pole. Yeah, because all these for all these integrals to converge, uh, yes, we need to take the intersection of the individual ROCs. Yeah. So is that clear, or am I causing any confusion?
It means that
Sorry.
for the convergence, we are checking the conditions, like for causal system or any system.
Yes, for right now I'm showing for causal, but yeah, using the same argument, it follows for anti-causal also. You just have to take the left-sided part. But yes, go ahead with your question if there is any.
Oh, no, sir. It's clear. Thank you, sir.
Okay, okay. So I hope you guys are able to make sense out of this. Okay, this is not uh, too difficult to understand. Okay, if you understand these examples, so this is for those who are still feeling confused. Yes, this is everything follows from these cases. So just consider the case where there is only one pole, and causal and anti-causal case, and both sided case also, and the case with multiple poles just follows from that. Yeah.
So, so the causal means the xt should be 0 when t less than 0, right?
Right.
Here you are saying that xt is causal, so shouldn't the minus p1 be greater than 0? If not, xt cannot be causal.
Wait, which one are you referring to? This figure? Which figure? Okay, so I'll write this again, and yeah, you can then chip in with what do you want to say. So
So I'm saying that if x is causal, then it shall be 0 when t less than 0.
just give me a moment. So Okay, so this is x is causal. Okay, now
Then x is 0 for t less than 0.
0 for t less than 0. Sorry.
But
Yeah, that's correct. Yes.
in the previous slide, you took the region of convergence is minus p. I mean, real part of s greater than minus.
Okay, okay. No, no, this is not t. Okay. There is no t in here. Okay, so this is s plane. Yeah, this is real part of s. So this is sigma. And yeah, if I have j omega axis here, so yeah, this is j omega. There is no t in here. Okay, so ROC is the region of the complex plane, S plane. Yeah, so ROC we are identifying in S domain. So this has nothing to do with right side. Okay, so there is no time axis in here. Okay, so yeah, there is a relation with right sided and left sided, but yeah, in the S plane. So yeah, when I say right sided in time domain, yeah, we mean something like this. Okay, so for exponential you have t identically 0. So this is in time domain, and this is the signal x, for example. Okay, so the signal is identically 0, but ROC is not with respect to time domain. Yeah, it, it makes no sense that ROC is whatever right or left of something. Yeah, ROC makes sense in S domain. Yeah, so
So then in the previous slide,
yeah, in the previous slide, this one or which one?
yes, sir. Here you said that, no, sir, slide 11. Here you said that it is causal if a real part of S is greater than P1. So how are we relating that causality with this S plane?
Uh, yeah, so okay, right. So let me explain this. Okay, so let me. So suppose I have a causal signal. Let me not bother about sign of A. U of t. So this is a causal signal. Then what I want to say is for causal signals, ROC is always like this and vice versa. If ROC is like that, then my time domain signal must be causal. Okay. So now if I apply the definition of Laplace transform, what I get is S minus A dt, and this integral is from 0 to infinity. Okay, so for this integral to be finite, so at plus infinity, depending on the sign of the real part, this integral will converge or diverge. Okay, so we want real part of s plus a to be strictly bigger than 0. If we can ensure that, then this integral will always converge. Yeah. So in other words, if real part of s is strictly bigger than minus a, the integral will always converge.
Here it shall be S minus here.
Yeah, yes, minus a. And here should be plus a. So real part of s, if it is strictly bigger than plus a, then uh, the integral will converge. Yeah. So everything to the right of your pole A belongs to ROC. Okay. So from causal signals to here, I hope it is clear, right? Why ROC is like this?
Yes, sir.
Because yeah, you just want to make sure that real part of S is strictly bigger than A. Yeah. And going from this direction to this direction, so why ROC? This implies causality. So this ROC implies that if I take any sigma, so any s whose real part is bigger than a, my integral is converging. If I take something which is whose real part is less than a, then since this does not belong to ROC, my integral diverges in this region. Okay. But it converges in this. Yeah. So that means that yeah. So everything to the right of this is in ROC, and if your signal is not causal, okay, so it extends to minus infinity. So t going from 0 to minus infinity, if it extends, uh, had that been the case, you should have this part within your ROC, but it is not. Okay, the ROC includes all regions to the right of this. Okay, so for those values of s, the integral converges. So your signal has to be causal. If it had not been causal, then yeah, you should have had the left of a within your ROC. If you take your signal to be not causal, is that okay?
Yes.
Okay. All right. So yes, you can also think about it a bit and yeah, possibly debate also. But yes, this identification I hope is clear. Okay. For causal signals, you get ROC to be of this kind, right half plane, and if your ROCs are of this kind, yeah, everything to the right of some axis, then your signal is causal. Likewise for anti-causality, and yes, if you have this finite strips, then your signal is mixed. Both causal and anti-causal parts are there. Okay. And you can get empty region also in general. Okay. So yeah, we are almost running out of time. So yes, this other properties also we have discussed actually. If xt is, so let me just read it. Yeah. If xt is right-sided and if real part of s is equal to sigma naught is in the ROC, then everything to the right of sigma naught is also in the ROC. Okay. So that's just restating this. Yeah. So if, for right-sided signals, we get ROC to be of this kind. So if sigma naught, okay, if this is in ROC, then everything to the right of sigma naught is also in ROC. This is what fourth property says. Fifth says the same for left-sided signals. So yeah, just this thing to the left of this point. Sixth part is for two-sided. Then ROC consists of strips that includes the line. I think I have left it incomplete. So yeah, let me rectify this. So for two-sided signals, yeah, you have strips like this. Okay. So everything within this strip is in the ROC. Okay. So if you have sigma naught like this, okay. So let me write that somewhere. I have left it incomplete in the note, but yeah, I will write it here. So suppose these are your extremes, okay, P1 and P2. So P1 real part of S strictly less than P2. So this is the ROC for two-sided signals. And if we take any sigma naught, so this property is there in the book, you can check that. If sigma naught is in the ROC, then everything to the left of sigma naught, which is greater than P1, this is in the ROC, and everything to the right of sigma naught, which is less than P2, is in the ROC. This is what sixth property says. I forgot to complete it somehow. Okay. So sorry about that, but it is there in the book. Okay, you can see it in OpenFind. Okay, so let's go to seventh one. Yeah, if x of x is rational, then ROC is either bounded by poles or extends to infinity. Yeah. So this is again this same thing. So it is one of these five types. Yeah, our ROC. So for right-sided signals, it extends to infinity. For anti-causal signals, it extends to minus infinity. For both sided, yeah, it is bounded by the poles, and yeah, it can be empty or the entire complex can plane also. Okay, so yes, if Xs is rational, ROC is either bounded by poles, like yeah, these three cases, or it extends to infinity, yeah, like in these cases. So yeah, here it is infinity, and here it is empty. So maybe tomorrow we will do some example where the ROC is empty. Okay, so eighth one, the last one, Xs is rational and Xt is right-sided. Yeah, this we have already seen. Region in the S-plane to the right of the rightmost pole, and if it is left-sided, then ROC is everything to the left of the leftmost pole. Okay. All right. So yes, we are almost out of time. I wanted to finish this today, but somehow I couldn't. But that's okay. Maybe I will finish this tomorrow. So Laplace transform properties. Any questions, by the way? We still have 2-3 minutes. So, yeah. One or two quickly we can do. Maybe 1 minute or so. First one I think we can do in 1 minute. I hope this is fine. Okay. The discussion regarding ROC. Also read it from the book. Okay. It will make it more clear. Okay. So properties, yes, I am going to discuss some of them. So this differentiation and initial and final value theorem, that I will discuss. Linearity, convolution, multiplication, those things, yeah, I'm just going to refer to continuous time Fourier transform. Yes, any questions? Yeah, so let me quickly do linearity. I've already seen that. So this part is straightforward. Yeah. Why ROC contains R1 intersection R2 and not equal to R1 intersection R2. So this part is fine, right? This is definitely contained within ROC. So R1 is the ROC of yeah, this component x1t. R2 is the ROC of the second component. And for the sum to converge, we need to take intersection of R1 plus R2. Yeah. So this is fine. R1 intersection R2 must lie within ROC. But can you think about any cases where it is equal to or not equal to? Why it is? I mean, is it a strict subset or we should have equality? Any opinion or any comment on that?
May or may
Sir, we
not
can
be.
take the function.
Yes, may or may not be. So, or what was the second second comment?
Sir, we can take a function e to the power minus 80 times ut, which has a ROC which is a subset of C, and we can take another function delta u minus e to the power minus 80 times ut, and the sum of those will be delta t, which has a complete C as ROC, but individually they don't have a common intersection.
Okay, I missed. I could not get like everything about what you said, but yeah, idea is correct. Yeah, you in general, you can have a signal where yeah, the ROC is the entire complex plane. So I missed out on one or two things which you said. But yes, you can type it maybe in the chat box, or yes, you can send a snapshot so that everyone knows. So I'm going to give another example, so which is a trivial one. Okay, so you just take x1 minus x1. Okay, so this is my x of t, which is 0. So R1 and R2 are the same. So R1 intersection R2 is again R1. But since this is 0, its Laplace transform is 0, and ROC is the entire complex. Okay, so this is a trivial example, but yes, one of you have given another example also. Yeah, all of you can see. Okay, so let us stop at that. And yeah, I'm here for questions for a minute or two. But yeah, you can leave. The class is done. Thanks for attending.
Thank you, sir.